This is House Planning Help episode 386. Hello, I'm Ben Adam Smith, and this is the podcast for you if you're interested in building new or retrofitting an existing property. We're exploring what houses we should be building in the 21st century and trying to break down the major roadblocks that may get in our way. Coming up in this session, my guest is Joshua English, co-founder of Okom wrks. We're exploring the potential of mycelium-based composites. Could we be growing structural mycelium in the future? Now, this may not come as a massive surprise, but building a new home or retrofitting an existing property is a lengthy process. It will probably take years, and we've been around 13 years. We've just celebrated a birthday, and so we've seen plenty of people get to the end, which is fantastic. And what tends to happen is they stop learning, they switch off, which is totally understandable, and just enjoy their lovely homes. But I wanted to put a shout out there if you are someone who is just about still in our orbit, or maybe you're getting towards the end of construction, don't forget about us. I have a favour to ask. Can you get interactive and share your top 3 tips? You've done this entire journey, and I would love to know what you've come out thinking at the end. It doesn't have to be long, or it could be a bit longer if you wanted to, but just 3 top tips. You can write it down, email it, you can share it on social media, you can record a voice note if you want to. Just head to houseplanninghelp.com. We've got all the information there of ways to get in touch. We used to do this feature, and then for some reason it just stopped and we forgot about it, and I'm remembering again and trying to reinitiate. So if that's you with some useful information, please pause the podcast here, go and think or make a note to help Ben out. Lovely, thank you. Let's get to our featured interview with Joshua English, co-founder of Okom wrks. We like to mix it up on the podcast. We're all about sustainability and we focus different episodes on different materials and products, but you're probably unlikely to be using this one anytime soon, but they're making great progress. So I thought, let's find out about mycelium-based composites today. And Joshua's our man. I started by asking him to tell me a little bit about his background.
Yeah, I have one of those jack of all trades, master of none. The full quote on that is oftentimes better than a master of one, which I like to remind myself of. My early professional life was spent doing database programming. I was an artist, went to school and got an art degree, and found that numbers were one of my favorite media to work with. And so was working in that, did a long stint doing actually data analysis and data visualizations for healthcare for 18 years. During that time, I started to miss the physical world. Everything I did was in ones and zeros. And so I went back to school and got a degree in interior architecture and design. And I had an emphasis on industrial design. It was available to us in the degree program that I was in. Having a focus on that also led me to really have a hyper focus on materiality. And I really wanted to try to find the most sustainable way to build things. I'm a longtime carpenter, love working with metal, love concrete, but, doesn't take much to figure out how incredibly terrible all of those materials are for the environment. And so I was on this long quest to try to find the most sustainable material that I could find. And a friend of mine, we were at a design conference, and he mentioned, have you heard of mycelium-based composites? I also have had this lifelong obsession with fungi, and so had never heard of that before. This is rewinding about six years ago. Did a deep dive on that and was just really trying to see if I could be using existing kits, technology, whatever is available, trying to see if I could be the first designer to design a chair that a human could sit in using mycelium-based composites. You would find a lot of chairs, pictures of chairs made out of mycelium-based composites, or they would have mycelium-based composites incorporated in them, but you would never see anybody sitting in them. So I thought, okay, this is a great opportunity. And my friend said, great goal, never going to happen. It's just too soft. Good luck to you, though. So I went and squirreled myself away for a good 6 or 7 months, really trying to figure out how in the heck that whole technology came together. Got some material, gathered all the information I could, scraping it from the internet, and made a mistake in the lab. Actually, I had a process, because my research background, I figured, I'm gonna take about 2 years to see if I can research the best possible way to make mycelium-based composites stronger. And during the first set of experiments, I had a bunch of extra material left over. And so I just was looking around the house. I was like, well, what do I do with this? I'm going to do this. I didn't want to waste the material. It was expensive to obtain, took a long time to make. And so in that mistake, or kind of just random, hey, let me see if this will work, it ended up being the trick. And then had to kind of reverse engineer that mistake. And fast forward a few years after that, I was able to successfully patent that process. We're currently in the process of patenting the material itself, and we're trying to make a business out of it. And it's not the easiest thing to do.
Well, respect to you. It sounds incredibly difficult. I think we've got some beginner level questions, first of all. When we're talking about mycelium, what really is it and what's its history? How long has it been around for? And then what are you adding to it?
Well, fungi, the kingdom of fungi, often gets confused with the plant kingdom. Oftentimes people think it's some kind of subset of the plant kingdom. And it is not. It's its own whole separate kingdom where animals engulf their food and plants photosynthesize. Fungi have developed this lifestyle where they absorb their food. So their whole lifestyle is centered around surface area. So when we talk about mycelium, the mycelium is, when I think mushrooms, when I think fungi, I think mycelium, because that is by far the vast majority of the organism is the mycelium. A good analogy is that if you think of an ant colony, that is the mycelium. And the individual ants are these components of the mycelium known as hyphal strands, or for short, hyphae. And so a mycelium will have millions and billions of hyphae, sometimes even trillions of hyphae that branch out and explore the environment and provide surface area so that they can exude their enzymes and then absorb their preferred food source. Because of their lifestyle strategy, those hyphal strands need to be incredibly strong, they need to be durable, and then they also need to be kind of multi-use as well. And so we can exploit that capability of the fungus to create an adhesive part of the matrix of a composite material. And not all fungi have the capabilities to create strong mycelium-based composites, just like the animal kingdom, where you have everything as small as ants all the way up to an elephant. In the kingdom of fungi, you have that same kind of diversity. And so far, what the designers and mycologists who are trying to look into this have found is that the types of fungi that tend to grow on trees are particularly well suited for this. And the reason for that is that there are a few different types of morphologies or ways that fungi can build hyphal strands. They're kind of like stem cells, where they can start off as a stem cell and they can become a lung or a bone or what have you. And so same thing with fungi, they can create different types of hyphal cells. However, there are only a certain very, very small subset of these in the kingdom of fungi where those hyphal cells can be made into 3 different types. Those would be generative hyphae, which all filamentous fungi make. And then a very small subset will make generative hyphae and skeletal hyphae. And those skeletal hyphae do exactly like they sound. They provide structure and form. And then a third, exceedingly smaller subset of the kingdom of fungi will make a third type of hyphal morphology called the binding hyphae, which does exactly like they sound. They provide like a glue for all 3 types of hyphal morphologies. And you can see this in the forest when you see a terrestrial mushroom growing up out of the soil. They're soft. You can easily crush them. Typically, terrestrial mushrooms only contain generative hyphae. And then if there's a little bit more of a toughness to it, maybe that one also has the second type, the skeletal hyphae, and those are a little longer lived. And then if you've ever seen those bracket fungi living on the sides of trees, those can and tend to have that third type. So the generative, the skeletal, and the binding hyphae. And those are durable structures. They can live for 60, 70 years. I found Ganoderma and Aplanatum species in the forest that they create sort of annular rings. Every year they'll grow another new surface underneath the one before, and it creates this large structure. And you can count each layer to see how long that fungus has been in that forest. And I've counted up to 60, 70 layers of those types of fungi. So if you can imagine, those naturally drive researchers into thinking, well, of course, those are the best ones to use. And they are so far. Having said that, in my work as a senior mycologist at the farm that I work at, I get to work with a lot of different type of fungi. And I'm always surprised at how strong even mycelial colonies can get. And so I think the future is still wide open in this. We are such at the nascent stages of understanding how fungal mycelium-based composites come together.
So this does sound, as you've just said, in the early days here, but how do you know what to do? Is this very much just experimentation as you go along, or have there been some big breakthroughs?
Yeah, it's a very good question. The technology really does predate the early 2000s, but about 20 years ago, somewhere in that time frame, there was a gentleman by the name of Philip Ross who was an art major at Stanford. And he was also, like me, kind of this lifelong mycophile, and he had been growing mushrooms in his garage for a long time, and then just started to realize they're kind of beautiful. These mycelium blocks can take on these characters that are kind of interesting. And so he started to have that be his art medium. So he started to develop processes to make things, not necessarily food, out of these mycelium colonies. And he was publishing a lot of his findings online. It was near the advent of YouTube. He was putting the information out there for all of the other mycophiles, and people were kind of taking notice, and his structures and his artwork that he was doing with it was really striking. Then there were some students in New York, some engineering students that had heard of this as well, and so they had taken the challenge at school to develop a business model using this type of technology. So they figured out, well, we could make a foam packaging replacement. So they decided to try to commercialize that. And this is going back about, maybe 13, 15 years ago. In that time, from about 13, 15 years ago to about 6 years ago, there really wasn't a lot of information to go on. The information that you got was really scattered throughout all of the various forums that you could find. And it was really hard to get one place to find all the information. One reason was because that company that came along to try to commercialize it, they started patenting a lot of the technology. So they obviously weren't sharing their tips and tricks on a wide scale. But they were also building these grow-it-yourself kits, which did allow you to use the material and figure out what to do with it, kind of in the hopes of, hey, figure out what you could do with it and let's see where it goes. In about 2013, 2016, you had researchers starting to pay attention to this. And so they started to take a look at what are the structural qualities of it, what are the other qualities that we look for, certainly in the building materials world, water uptake, fire retardance, ability to stave off contamination, molds, all that kind of stuff. And very interesting findings on like fire degradation, sound attenuation, really great at sound attenuation, but really poor in structural mechanics, really poor in water uptake. And so basically there was a lot of interest in it. And then so people thought, okay, let's just relegate these to things like insulating panels or just decorative wall sound mitigation panels. And then let's not even think about structural materials because they were about as strong as styrofoam. And so I hadn't heard of any of that research when I got into it at first. So when I first started to deep dive, I went through the literature and realized, oh my gosh, this is it seems like a long road to hoe here. And interestingly, too, at that time, it was easy to get through the literature because there's probably like 20 papers in 2019 when I started researching this. But what happened over the time, as the years went on, you would see this exponential increase in the number of papers that were written. People wanted to relook at moisture uptake and see if could they add something to it to improve that quality. Certainly, people trying to improve mechanical strength was also a focus, trying to see can we create 3D printable materials that can be used that way. People trying to perfect techniques for creating sound mitigation panels or any kind of insulating panels. And so you would see this exponential increase in the number of papers till today. You have hundreds of papers that are available in the literature and also some pretty significant advancements in the technology. And so now you actually have people now getting their PhDs in mycelium-based composites, which is pretty interesting. Belgium seems to be leading the way in that. Several folks have come out of the University of Ghent and have done some really interesting research with this type of technology. And then you have a guy like me who makes a mistake in the lab and then finds this way to make what seemed to me to be structurally sound materials.
So what are you doing on a day-to-day basis? Are you starting with this vision of what we would like it to be? And as you say, you come across this mistake, which is very, very valuable. But, how are you driving it forward? How are you funding it? You said that was a challenge, turning it into a business. How's it all going to work?
It's not going to work until we can show the venture capital folks that the timelines involved in this type of research are not like 1 or 2 years. It's more like a 5-year plan, 10-year plan to get to commercialization. I also think that because it's so new, that we need to not be siloing and trying to commercialize right away. And that is kind of what has happened. It really is the Wild West. The first person to get a PhD in mycelium-based composites is a woman by the name of Dr. Elise Elsacker. And one of the most interesting things in her PhD dissertation that I thought was the biggest take-home for me was she mentioned, this is really the first time in material science where we've had a material make it to the marketplace without really any fundamental knowledge of how the organism interacts with the material or how really what the long-term consequences of the material are. So basically saying we've been putting the cart before the horse here over and over and over again. You've also had a big rush to patent these types of materials. Guilty as charged. It's kind of one of those things that you've got to, if you don't want to be overtaken or bamboozled or, taken advantage of, you've got to play the game. And so I think that series of unfortunate events has really led to kind of a stifling of the technology. And then you have people making wild claims. I would say saying that you have the world's strongest mycelium-based composite, like we say, is one of those wild claims, but we like to back that up with data. And there really aren't any standards as well for how we measure, how we create these things. And so I think that the way that this technology is going to move forward is by really combining forces, encouraging the universities to take these up, encouraging governments to subsidize this type of technology, because the capabilities really are endless, about as endless as the kingdom of fungi is. You can think of that many uses and applications for it. But it's going to take some standardization and some really targeted attention to how we progress along with the technology. So when you look at the literature, you see several different ways of conducting compression tests, using different thresholds, for instance, using different organisms, using different growth patterns, using different subspecies of all of these organisms. And so I think standardization is going to be one of the major keys to this going forward. But it's certain none of this is going to happen without funding. It's a really long, arduous process. I've put at this point about $250,000 of my own money into this, and I am currently tapped out and really trying to find those funders who can allow us to continue. We're in a somewhat of a pause right now because just the funding has really dried up for this type of material. We get a lot of really early interest. People think it's the coolest thing they've heard. We show them the material, we show them our data, and then we can even show them a business case for it. But it's just that 5-year timeline. That's what stops the conversations at that point.
It's always frustrating when you see the computer world, for example, and Silicon Valley seems to just get endless money poured in, and this could show a lot of potential. But yeah, same thing, it does need the investment. So just take us through, if you wanted to paint a picture of what is going on. Are we talking about growing? Is this growing all this stuff? And what would that look like? Do we have to do that in specific, almost lab conditions?
Yeah, so when we're growing a single fungal species, yes, we have to have some pretty significant sterile conditions to start the kind of the starter culture, if you will. And then as we're going through a manufacturing process to make materials, for instance, you do have to have a fairly clean facility. At a minimum, it has to be food grade facility type. So if you can imagine people who make SIP walls or the sawmill or anything, that is not in their wheelhouse whatsoever. So it is going to take kind of this hybridization of how we do it. But where I currently work for my job to make some money right now as a mycologist, we are an indoor farm. And so kind of like how farming has gone indoors, building materials manufacturers are going to kind of have to go outdoors. That analogy, we're going to have to kind of turn it inside out. One of the other most amazing things about this, the potential of this technology, is you can start literally from a single spore. And you can grow enough material from that single spore in about 90 days to grow enough for several houses. And so that is pretty remarkable. During that process, you start from a single spore, you put it on a petri dish, you grow it out a little bit, you add that to a little bit of material. The way that fungi will progress in captivity like this is you have to you can't just take one spore and drop it in a vat full of stuff and then hope that it propagates through. That would take forever. You have to kind of basically double the amount of material you introduce it to until a certain level, then you can kind of multiply that by 10. And so you build up, and all the while you have to make sure that the fungus isn't getting too old because its life cycles can be pretty rapid. It can go all the way from single spore to senescence pretty quickly. And then if you've got all that timing right, the way that I grow the material is basically in the open air. I don't use any kind of rigid molds, and I don't seal off the top to keep the contamination down. I grow them in basically a fabric forming process. And the most remarkable part of that process is that it takes 5 days to grow. It doesn't matter if I'm growing a 1 meter part or a 10 meter part. It's going to take 5 days to grow. And so during that 5 days, it's fully colonizing the substrate. It's forming a fungal skin around the outside of the material, which is very tough and durable. And then at the end of that process, you do have to dry it. And the main importance for that is to kill the fungus because you don't want to have that fungus continuing to digest the material. And then in that drying process is where all of the rigidity and the strength comes. So you're basically taking that mycelium at the end of its life cycle, and when you dry it, it hardens it into this matrix that is really quite strong.
So a little bit earlier, you said that you started out as someone who'd been a carpenter and saw that this was interesting. I know Chris Magwood is a big fan of what you were doing as well, and I admire his work. So if he's excited, I'm excited. So, have you had a chance to work on a building at all in any respect, even if it is just insulation, or are there early obvious products that can be useful, or little test cases?
Yeah, so we had done a project in New York City 2 years ago. It was a non-structural, just basically an experiment or a project just kind of showing, hey, these are mycelium-based composites. It had our textile reinforcement phase in there, but we weren't using them in any structural manner. The second half of that project was supposed to include us manufacturing some chairs, but the difficulties in finding facilities that would allow us to dry that material at that size and that scale really severely hampered that. So we've paused on that for quite a while. There are folks who have built very large structures that incorporate mycelium bricks, if you will. The Hi-Fi Tower is probably the most famous one of those. This was done at PS1 in New York City, where they built a very tall tower. Now, the caveat being that the structure of that was made with timber. And so basically they were just using the bricks to kind of close in the structure. And then there is a gentleman in Ohio who uses edible mushroom mycelium blocks. He compresses them down in a 20-to-1 ratio to make really, really strong materials. These are stronger than cinder block type materials, but certainly these are composite materials. Very different process than what I'm trying to develop, which is how far can the fungus go to grow these materials? And that includes, letting the fungus do all of the heavy lifting. We don't use any industrial compression. And so for us, what I see is I want to try to see how far this material can go by just letting the fungus grow through the material and then heat drying it at the end and seeing how strong that can be. The limitations of that for me right now is building a 3-meter long part that is about 300 millimeters in width. That's not a very big part, and I can really only make those one at a time. And it takes quite a long process to manufacture that. So we haven't had really the facilities available to us to make it at that scale. Having said that, there seems to be a lot more collaboration brewing in this mycelium-based composite world. So folks have been approaching us with various levels of space, technologies for drying that are allowing us to reconsider getting back to the place where we can, for instance, build like a SIP wall section, build things that could be like 2x4 replacements. It's important to point out, though, that if we were to build a piece that was exactly the same 8-foot long 2x4, it is not going to be as strong as that wood product is. Now, however, if we grow several of these parts together at the same time, that is, and cross-layer them, I have built a 2-foot by 2-foot SIP wall section that was incredibly strong. We did not get to crush that particular piece. We did some other testing on that one, always with the mindset of we'll make another one. And that make another one never happened just because of the difficulties. But one of the really interesting aspects of that SIP wall section that we built was that it was completely, all of the parts, there was 7 total parts, were all adhered together just using the mycelium itself. There was no glue. It's a real shame that we didn't get to test that in compression, because from what it seemed was that it wasn't just a 1 + 1 + 1 = 3. There seemed to be some kind of synergistic effect to them all growing together at the same time with that adhesive. So the goal is hopefully by the end of this year that we can find our way back to at least recreating that 2-foot wall, SIP wall section, and then going from there.
And I know this is all very early days, but is there some analysis of how much effort and energy input is going into all of this, or is it really not taking much at all?
There have been some really neat attempts at trying to find what this could look like from an energy input standpoint. And with my data background, I have made some attempts at this too, knowing, with the state of the art as we know it now, have done some extrapolations. And from what I could see is that basically we would be able to create so for instance, it's a material, it's stuff, not a thing, right? So we're making a stuff. It's like saying you're a wood salesman. No, you sell 2x4s, or you sell plyboard, or you sell SIP walls, So thinking about that product. So one of the things that I did when I first made this discovery was I reached out to Chris Magwood. I had several of his books on my shelf, and I thought, if anybody is going to be able to help me out here, it's Chris. Very early on, he said, hey, let's think about SIP walls. And so that's been the focus for us from the very beginning. And in my analysis, what I found is that we probably can create them in the very beginning at a full scale, if we were able to extrapolate this out, at a very cost competitive standpoint. So you wouldn't spend any more to make a SIP wall section, and you would have them be made out of mycelium-based composites. And then over time, we do believe that we could even make that difference even greater. What's also important to keep in mind is that by reducing the reliance on timber, by reducing the reliance on adhesives, by reducing the amount of water it takes and all of the energy inputs that it takes, those embodied carbon aspects of building materials, those savings that don't necessarily translate into dollars for investors but are good for the environment are also considerable. And so those are the things that we have worked on, and it's pretty promising when you look at those numbers.
And is it likely that the uses to begin with are totally unrelated with construction, but they might bring more money into the industry?
Yes, certainly. There definitely have been several attempts at creating businesses that create foam packaging, for instance. Mogu is a company in Italy that has been creating decorative wall panels, sound attenuating wall panels for a very long time now. And that has kept it in the zeitgeist. Really, after that, there have been several fits and starts at trying to commercialize this, but it's been rather difficult. And so I think that for us, like Le Corbusier said, chairs are like small architecture. These are small buildings. So, and I'm also infatuated with chair design. So I think that perhaps a chair, mass-produced, fully mycelium-based composite chair, can do the trick to show the industry that it can be done commercially, and to show consumers that you can put these things in your house. They're not going to grow weird things off the side. They're not going to infect you and turn you into a zombie and make you attack your neighbors, and that they will have some heirloom quality to them.
That had to be something on my list that I was going to ask you, is the health side. That is it healthy for everyone, or what about allergies to mushrooms and things like that? Or are we so far removed from that it's completely different?
Yeah, there are a few camps here in the mycelium-based composite world. Some think, wouldn't it be great to have these living buildings that can heal themselves? And it's great. I think that may be 100 years down the road, maybe 50, maybe, I don't know. It's down the road. The problem with that, like I mentioned, is that a fungus is going to need to continue to consume something. And so whatever substrate you're using is eventually going to be either fully depleted, so it cannot remain living, or it's going to degrade a structure. So you'll rob Peter to pay Paul. You can heal the building, but the building's also going to be falling down. And then so the important part of that kill step, like I mentioned earlier, makes it so that that fungus is no longer able to grow. If you do it right and you do it to the extent necessary, then at a minimum, that specific fungus will not continue to grow. We never grow, for composites that is, we never grow to the fruiting body stage, which means there's never any spores produced. So from that standpoint, it's completely healthy, because usually people have sensitivities to the spores that are produced by a fungus. The other issue is that most mycelium-based composites are incredibly hygroscopic, and they will just take up a lot of water. So any other molds or anything that would find this material in a wet state will then take over that material and start to colonize it itself. But if you have a material that is able to stave off that moisture, or you put it in a setting just like you would lumber, where you're going to protect it from the environment, or from the elements, that is, then you would have a system that should be just as long-lived. This is early days, absolutely hypothetical, but from what I see in our own research is that I think it is doable, and I think it is safe. And one of the reasons why is that 200, 300% water uptake is typical with foam-like mycelium-based composites. However, our material is far more dense without actually adding too much to the mass of them. And they also have instead water uptake in the ballpark of like 25 to 45%. So kind of a big leap in the right direction there. I think that there are improvements to be made there by improving the fungal skin, adding natural things like beeswax or something else that, my whole goal is to, if we can avoid any kind of petro-based products in this, that's great. Going back to that low-hanging fruit, though, is if in the beginning we can make the parts, but then cover them with something like a epoxy resin in order to kind of get the ball rolling, I'm actually all for that. I was very much opposed to it in the beginning of Okom Works, but as time went on, it's definitely softened to that idea.
Yeah, this word composite, what are we actually meaning, or are we just exploring at the moment? How much is the mycelium and what are we mixing in, or is that the trade secret?
Yeah. Composites have been around since the first mud bricks made with straw, so that straw provides that strength to the mud brick that normally wasn't there when it was just using mud alone. Concrete is another great example of a very commonly known composite material. And then I think a lot of people, when they think composite material, they think carbon fiber composite materials. So in our material, you have to have some kind of substrate for the fungus to grow on. I prefer using hemp for many reasons, but it's a very strong material, and it has several qualities that are beneficial. And it just so happens to also be very tasty to the fungus that we're feeding it to. And then the fungus serves as that adhesive phase that binds everything together. And so you're using these two different materials to create like a brick, but then I add in the textile reinforcement phase that then lends itself to even more strength. It actually improves the compressive strength by orders of magnitude over the foam-like materials. And then also, because of the nature of the textile, it also provides tensile strength to it that is also orders of magnitude better than those types of mycelium-based composites that don't incorporate a textile reinforcement phase. That textile reinforcement phase had been tried before I'd tried it, but it's notoriously difficult to get it clean enough and then to grow it in a way that doesn't get contaminated before the end of the grow process. And so that really is the trick there.
This strength aspect, is that going to unlock a lot? You've mentioned it a couple of times, and I've felt that you've highlighted it and that it's a clear direction, but over and above all of the other qualities that we've talked about.
Yeah, I think that the strength is where a lot of people, certainly architects that have been interested in it, they go, well, it's not that strong. So they get kind of, and even when we show them our data that are about 1.5 orders of magnitude stronger than previously published data, we're basically clocking in around just north of 1 megapascal in compressive strength. That is not knocking any engineer's socks off. And so you have to then think about how then do we reimagine how we use materials in this instance. And so it's kind of thinking differently about how you might build. So thinking modularly as opposed to just, kind of brute strength and pouring more concrete into something, and instead using geometry and genius engineering to build lighter, stronger structures. So anything that would make steel lighter and stronger from a geometry standpoint also would work with our material as well. And so I think that is the next frontier. It is also optimizing the way that the fungus grows. There are some genetic changes that we can cultivate in the organism that we would use to kind of enhance certain qualities. There's optimizing the growing conditions, which require very stable temperature, moisture, lighting conditions, air exchange in the growing chamber. All of those things can be optimized, and I think we're in a really great spot for that, because with the popularization of machine learning, I think that the number of variables that are involved, humans aren't able to process that. So using machine learning in conjunction with that, I think, can help us to accelerate this. So I don't think it's not going to be a linear curve. I think that we're going to see this logarithmic growth over time that's going to keep progressing. And one of the other benefits too is that people are starting, like I said, to kind of pool resources. So Phil Ross, who is a progenitor of mycelium-based composite technology, now has an organization, a nonprofit that he started called Open Fung, F-U-N-G. And the goal there is to create these baselines for researchers so that you're not starting from scratch to learn how to grow a fungus and then try to do the structural aspects of it. You're starting off with this kit that shows you, okay, here's how you do it, provide some training so that when you're starting to do the engineering side of it, you can go further faster. And so that enablement on that side is, I think, quite exciting.
And just as we start to wrap up a bit, we know money's a challenge. Are there any other challenges or things that if we could wave a magic wand, what would you like to do that would just accelerate us down this road?
I think having the mycology become a focus, certainly in US and Canadian universities, the mycology department is usually tucked away in the plant pathology department. It's only thought of as how do we control it? How do we get rid of it? How do we not make it ruin our crop? And so if we can pull it away from that and start thinking about mycology in the academic setting as the starting point, not as like something to combat, that's the first step. Europe is definitely a little farther along. And even in my own backyard here, we do have some universities that are starting to build these programs. That's really exciting. I think government funding is also quite necessary, and then also to find the appetite within the VC world. And I know that those both deal with funding, but I think that's important. The research component of it is also important. So having these find their way to national laboratories, for instance, here in the United States, where we can have really big brains working on several aspects of how we develop this material going forward. So in a perfect world, we'll have multiple major programs that will focus on just the mycology side, the engineering with the mycology emphasis. That to me is a true perfect world, because when people get degrees in something, they're going to want to work in that industry as well.
And what about energy levels for you? I know when you start off on something so big as this and you pour in your own money, can you keep on going? Is this still exciting you and driving you forwards?
Yeah, I like I mentioned, I had a lifelong obsession with fungi. And then I started a business where it was everything I thought about. I definitely hit a wall about a year ago. That was really difficult. I had been on the road doing research for a couple years. It really started to hamper my personal life, definitely my financial well-being. But thankfully, I was able to, because of my connections in the mycology world, was able to find a way to be gainfully employed. So I've been basically taking this gap year, but it's wonderful that I've been able to stay in mycology and continue to hone my skills on that front, which has actually started to kind of reinvigorate me to think about the next steps to move back into the building materials world. In the very beginning, a lot of the pressure was I wanted to be first, and I thought for sure that during this gap year, if you will, somebody would have come to market with something. But it really is inspiring to think that, okay, the work that I've done still is at the forefront, and I want to get back to that now. I'm really starting to itch to get back into making building materials. The employer that I'm working for right now has a facility that they currently aren't using. It was one of their earlier production facilities before they had several expansions. They've been holding on to it, and when I went and toured that facility, the first thing I thought was this: if I would have had this facility 5 years ago, we would be having a different discussion about the next building that we're building with this. But it's exciting to know that not only am I getting my energy level back, but I think the infrastructure might be there for this next step, which I'm ready to start tackling here in the next few weeks, actually.
Good for you. Keep it going. Is there a final thought, or do you want to underline anything from our conversation today?
Yes. Just as diverse as the kingdom of fungi is, so are the applications. And so it's just like with all things in building materials, whether it's industrial design or architecture, The material has to match the job that it's meant to do. And so that's first and foremost very important. The second thing is to not oversell the capabilities. The truth is stranger than fiction. So let's just stick with what truly the fungus is capable of doing, and let's not oversell it. Let's not build unsafe structures. Let's not build structures that are going to stand for a few years and then turn into a soggy, wet mess later. Let's make sure we keep honest about it and then also keep enthusiastic. And I think as well, this is a call out to all of my other colleagues in the field. Let's think about ways to share. Certainly patenting is important to gain investment, but let's think about how we might be a little more collaborative in the field. And that would be my request to those mycologists and engineers who are currently exploring these ideas.
Joshua, it's been fascinating, a whole new area for me, and it's always interesting where sustainability leads to these different paths. So thank you very much.
Thank you, Ben.
Head online to take a look at the show notes for this session, houseplanninghelp.com/386. We've got a summary waiting so you can dig into the details again, some photos as well, so you can put visuals to our conversation today. And maybe you've got a comment or you'd like to ask a question, where we've got social media links worked into the show notes, along with links to Joshua, to Okom Works, houseplanninghelp.com/386. Let's finish up today with a request. If you enjoy the podcast, we would love a review. And this helps signpost the way for others who are maybe starting out on their journey and they need to stumble upon some good information. Hey, that's us. Creating healthy, comfortable, energy-efficient homes is what we're all about. So it can be a few sentences or a bit longer. Explain what you think it is that we do and how we help. And we'd love to read that out on a future podcast as well. So a review on whatever app you're listening upon. Thank you. Next time, Will South from Etude is my guest. We'll be hearing about his retrofit in Brighton. Thank you so much for being there. The House Planning Help podcast is produced by Regen Media, content that matters.